this is an introductory talk about ion beam analysis techniques. My name is Milko Jakšić. I'm head of the laboratory for ion beam interactions at the Ruđer Bošković Institute. And the key instrument we have are two accelerators, which are situated in Zagreb, Croatia. So you can see this is a picture of one of the accelerators and the crew of the laboratory. Most of the facilities are actually dedicated to ion beam analysis. So I will just start a little bit about accelerators, or that is, although this is not really maybe in the focus of this school, but accelerators are used in many different areas. Mostly they are used in medicine and industry. This here is a sketch on the right side. You can see how evolution of the energy of particle energy that accelerators deliver has been evolved in almost 100 years now. Well, in 90 years from the first accelerator in 1930 by Walton. So the first accelerators were kind of rectifiers and electrostatic generators, which is basically the same principle we are working on in our accelerator. You will see that later. And as one of an important part of the HERCULES school is also electrons, actually a light source. These are here electron synchrotrons, which are one of the very sophisticated instruments. So although all these high energies accelerator were produced in decades, you can see even linear increase of the final energy. Still, the most used ones, the most applied ones are these at the very low energies scale. For instance, about half of the, maybe 40% of small accelerators are ion implantation accelerators, which are actually small implanters used in semiconductor industry. And yeah, okay, so I will start backwards from the way how actual accelerators are operating. You have AC basically and DC, so that you have alternative current or direct. So in the cases of alternate current, you have to have a pulses, and pulses of charged particles, which are electrons or different ions, are kind of riding a wave along the H3 potential, which is either linear or circular. Here is an image of the electron synchrotron, like the one in Electra. Or you have a small linear accelerator, so okay, they can be even sometimes 100 meters long, that accelerate electrons or ions in this way. So the same kind of riding a wave of potential along the tubes. As particles is getting faster, then these cylinders are getting longer. And with this kind of linear accelerator, it's easy to reach something about 100 mega electron volts. In the case of electrostatic accelerators, there are only two basic ways how to produce the charge, how to produce the megavolt potential. One is, most of you are familiar with Van de Graaff generator, which is a very simple mechanism. Positive charge is transported to the insulated terminal at the top, and they are, as the charge are grouped at the outside of the sphere, they are charging slowly, transporting the charge from negative, from the ground potential up to the ball. So one of the important things is that with this very simple mechanism, you can produce 1 million or few million volts easily. And if you look at the energy that 1 million volts can give to, let's say, protons, it gives velocity of 16,000 kilometers per second. So basically, these ions of protons, for instance, are very fast, and therefore they are very powerful when they are entering the material. And that's the basic of the ion beam analysis techniques. So in the case of accelerator in Zagreb, and majority of accelerators of that kind are operating in kind of tandem principle. So you produce the positive terminal voltage. In our case, this is up to 6 megavolts, but normally up to 4 megavolts. And then you have to produce negative ions, which means, for instance, if you want to accelerate at the end protons, you have to create hydrogen negative ions. And this is done in most easy way by the beam of cesium ions, which bombard the target where there are our elements that we want to accelerate. For instance, if we want to accelerate hydrogen, we use titanium hydrate. And then these cesium ions produce a lot of different ions, and only the only the negative ions are accelerated towards the accelerator. And then when these negative ions are accelerated to, let's say, 1 megawatt potential here, so they get 1 MeV energy, they will they go through the stripper channel, which converts by collisions with low pressure gas. They are converted to positive ions, and then again they are accelerated by another 1 megawatt potential difference, which means that 1 megawatt at the terminal will give 2 MeV energy for protons. And then we analyze this beam and direct it to the scattering chamber. In reality, this looks like this inside of the tank, which is normally, this is just during the maintenance period. So this is the terminal, and these are equipotential rings inside of the accelerator. After acceleration in the beam tandem, beam can be directed to one of the beam lines. So we have 9 end station, 8 beam lines, and 2 accelerators. So 1 megawatt accelerator is giving the beam from this side, from the left side, while the 6 megawatt machine gives from the right side. And in most of the chambers, they can accept both, either beam from one accelerator or from another. Contrary to the synchrotrons, that can operate only, that all the beam lines are actually getting the light, we can operate only at one particular beam time at a time. Only we have 2 different beam lines, this E3 and E4, which can accept 2 beams in the same time. And these two chambers are used for study of the fusion materials, because the fusion materials actually cannot have, because of the reactors are not working yet, so there are not sufficient density of radiation in reactors. So therefore, accelerators had to be used to mimic the conditions that will be once in fusion reactors. So we use this normally to mimic neutrons by the self ions and helium or protons, which are normally also used in fusion. Then all other beam lines are dedicated basically for ion beam analysis. We have also microbeam, but a little bit later about that. So these are, at the picture, these are different end stations for different purposes. So the basics of the ion beam analysis is trajectory, the passage of ions through material. So what happens when fast proton, for instance, or ion, like this is a picture of oxygen ion in silicon, is going through? As you can see, ion more or less maintains its direction, and all these small red points are actually individual ionizations. So by each individual ionization, ion is losing energy and creating some effects in material. Then you see also this green less dense events. These are scatterings on atomic nuclei in the sample, which are not that well, they are less frequent, but they are quite a lot. And you can see that these ions are remaining this trajectory, and they are all stopped in certain volume. And then this is a picture. We made the photograph. We left the beam into the air, and then you could see when the beam is high intensity enough, when the darkness is also good, that fluorescing of light, which is product of ionization in the nitrogen, actually gives you this nice image, which is completely the same as the one which is simulated. This shape is basic. One of its ion implantation, because you implant ion at certain depth, and also you probably heard about hadron therapy. This is the basic of hadron therapy, because this last part of the ion trajectory makes the most of the damage in material. So also very suitable for treating tumors in a human body. But what is not mentioned here yet are nuclear reaction. This is the third product, which all these three products can be used for some purpose. Either to modify material properties or to analyze the composition of target. I will not today speak about ion beam modification of materials, which is one very important application of these accelerators. This is just the only slide to indicate what can be done. Ion implantation, I mentioned already 2 times, is one of the most important. So you have to, you force the foreign atom to be injected into material. So something that chemistry cannot do in some cases. Then you have, if you have very high energy ions and they are heavy, they create a huge trajectory full with defects. And these defects can be then used to create, for instance, nano holes, or by negative resist, you can make, you can fill these holes with some metal, so make nano needles or nano helics or something like that. You can also irradiate with the protons to create much homogeneous damage. This is one micro machining picture of Stonehenge, done at, let's say, 100 microns or so. So there are many different applications, but as I said, that will be left for some other purpose. The ion beam analysis is based on the fact that today we very well understand the nature of the physical process that occur during irradiation of material. And then if we are able to detect the products of which are emission from the sample, we can make a spectroscopy, which can be either energy spectroscopy or mass spectroscopy. And then as the basis is of the analysis technique is understanding of the process, in most of these cases, we can easily make quantitative analysis of the elements present in the sample. So, as I said, there are many different groups of interaction. One is ionization, and one of the product of ionization is emission of X-rays. Then we have a scattering, and there are 2 techniques, Rutherford backscattering and elastic recoil detection analysis. And there are also nuclear reactions, so these 3 groups of techniques I will discuss in the next 10 minutes. So the ionization of atoms is based on the collision of protons with atomic electrons. And for the X-ray emission spectroscopy, it is important that this interaction creates a vacancy in the inner shell of the atom. And then as inner shell vacancy is created, by de-excitation, X-rays of characteristic energy are emitted. This is a level scheme for the X-rays, general one. And if you want to look at by some detector, in our case, this is conventional silicon lithium or SDD X-ray detector, you can observe different lines. Each of these lines are corresponding to one of the elements, and as you can see, they are ordered as the atomic number. So from the, let's say, here is the lowest element, sulfur, going up to potassium, calcium, titanium, vanadium, and so on. This is example of the particular matter, but tomorrow all these techniques you will have an opportunity to get information in much bigger detail by colleagues from my laboratory. Okay. There are also L lines, so there are K alpha and K beta lines. For instance, you can see iron K alpha and iron K beta. There are some here lead lines. And what is important also that the background in PIXE is very small. So Bremsstrahlung is quite small, and advantage of PIXE over other X-ray emission techniques is in rather low background. There are also possibilities to analyze these X-rays with much better resolution with the crystal spectrometer for fine structure analysis and possibly chemical analysis, chemical effect analysis, but we don't have time to speak about that now. So, as I said, the beam is directed over the sample, and you have to put X-ray detector very close to the sample. This is one simple arrangement of the external beam, so we could put the beam outside of the vacuum tube. This is exit 4, which is typical of aluminum or silicon nitride. Here is this beam is directed towards the sample, which was a plate of some Roman silverware, and here is the detector. And as you can see, the spectrum is rather simple. There are just few elements. These are L lines of silver because it's a silver plate. There is a copper, there is gold, very small, tiny peak here. There is a sulfur, and I guess, yeah, also a mercury, which is rather small. So this is the picture of the spectrum, but you can couple these spectra with position. If you can scan, for example, we can scan here the object over the beam, and by slowly scanning the object over the beam, we can extract these images and then identify the origin of certain structures, or in this case, of technology of how this plate has been modeled. Okay, the other possibility that we have in Zagreb is mass spectroscopy. So apart from the X-rays or light or many different photons, ionization could lead that the molecules that are ionized at the surface of the sample, so very surface, are desorbed. And if by applying the extraction voltage, some voltage that can accelerate these emitted ions, we could analyze their masses. So this is done by the time of flight, measuring the time of flight from the impact of the ion to the detection. And this is one of these spectrometers. We have two of them at one of the beamline with the capillary focusing. We have this mass spectrometer, and we can see these are masses up to, let's say, 600, and many different masses could be observed. This is rather new technique. There are just 3 or 4 in Europe, and we believe that this could be quite important for analysis of especially with the microbeams, when you can focus the beam to sub-micrometer scale. I don't have time much to speak about the details of this technique, but I will show you just one example. As it is surface sensitive technique, you can observe which one of the emitted molecules are coming from the surface. So this is a scan by the microbeam over the 2 inks, and this is for forensic study. The position of ink was of interest, And you could see that in two cases, here is the red one is over the green one, and here's the green one over the red one. So there are two different examples, and this is just a feasibility study to prove that some of the molecules that are associated with particular ink could be identified in this way. So the next process that we could use for the analysis is elastic scattering of beam ions. So the beam here on this animation of helium is reflected, is scattered from the atom nuclei, but there is also possibility to recoil the target nuclei. So in this basic kinematics of the scattering, where there is no energy released, so there are just conservation of energy. If you know everything about your incoming particle, so mass and energy, you can determine by detection in particular angle the mass of the unknown nuclei. And this is done by simple kinematics formula, and that is quite easy to perform. Also, advantage of this scattering is this is Rutherford backscattering spectrometry, which means that we can calculate the probability of scattering, and this is a cross section for this process. So cross section is actually probability that some ion will be scattered in particular angle, scattering angle. And on the basis of these two formulas, we can calculate the concentration of the unknown molecule. So both of these techniques that I mentioned up to now, with PIXE and RBS, are done in one very simple scattering chamber. The beam goes through the tube to the sample. This is a sample ladder where we can change many different samples. X-ray detector is here. Also, we have another one here. And here is a simpler Rutherford backscattering detector. This is simple silicon diode, and it can detect very well energy of the scattered ions. The most suitable for Rutherford backscattering are protons and alpha particles, and therefore PIXE and RBS are always performed simultaneously because this combination can give you much more information. So this is one example of the application of RBS, and this is also an example of from cultural heritage. In some of the ancient threads, so kind of religious, let's say, clothes, there are metals inside, and there was art historians were interesting to see what kind of technology was used in production of such metal threads. So here are two examples. One example is the lower one is green line is dedicated to gold, while the blue is for silver. And you can see that the gold is only a very thin layer at the top of the gold. On the other side, on the other example, this gold layer has been diffused into the silver, which means that the technology in these two materials was different. The next technique that is based on elastic scattering is elastic recoil detection analysis, and it uses the beam typically heavy ion beams coming from the accelerator to the sample, and then it recoils the nuclei from the sample surface into the kind of telescope, which is time of flight part and energy part. So we measure both the energy of the recoil ions and time of flight. In this way, for instance, this example is for 20 MeV iodine ions. We can see all different elements for hydrogen up to iodine in this case. So all the elements in sample can be visible. Also, you can observe here the depth profile. So this technique is excellent to measure the depth profile of elements in sample. There is no overlapping, so contribution from different elements is resolved. And this is an example of multi-layer sample of titanium nitride and aluminum nitride. You can see islands of aluminum, which are corresponding to the layers of, let's say, I think about 20 nanometer thickness layers. So this technique is extremely useful for depth profiling of light elements in heavy matrices. This is another example, which is also from cultural heritage, about the glass. Ancient glass turned to be pale, so it's not transparent as it should be. And this is the case. This is the reason for that is corrosion, glass corrosion. And as you can see here in the spectrum of glass, this particular one, sodium, which is important part of the glass, is leached out from the surface, while you have deposition of carbon at the surface. Sorry. And also hydrogen is deposited at the surface. So you can extract the depth profile of elements, and this kind of investigation is important to show how to prove what is going on with different kinds of glasses over the history. Finally, the technique that we do also is nuclear reactions. Unfortunately, nuclear reactions are not so probable. So only combination of beams and analyte elements can give you nuclear reactions. So typically, analysis can be done by protons, helium ions, deuterium ions, and helium-3. And they are ideal for analysis of light nuclei, like lithium, boron, and beryllium, and some others. So there are two possibilities. The first one is that excited nuclei emits the gamma ray, which is characteristic for particular nuclei, or you can have a reaction to emit the product, which is always either proton, deuterium, or helium ion, which are emitted from the particle, from the nuclei. On the basis of detection of these products, we see there are two types. Nuclear reaction analysis is actually the one the name is used for the analysis by detection of particles, while PIXE spectroscopy is detection of gamma rays. So this is one example of analysis for boron. Proton beam was used, and the very low concentration of boron was found in some optical fibers. And all this contribution at several MeV of energy came from the nuclear reactions. This technique can be very useful because it's, for instance, for analysis even of hydrogen, or for analysis of depth profiling in some materials. Concerning the gamma rays, typically we use germanium detector close to the chamber, and we have a series of different lines which are very well defined, very well energy defined. So germanium detector has excellent resolution. And you have a bunch of different reactions that you can use for particular elements. For instance, in the case of fluorine, you can use this reaction and these low energy gamma rays to profile, to determine, for instance, concentration of fluorine in teeth, which is, you know, that in teeth there is quite important, fluorine has very important role. So this is one of the examples. Finally, all these techniques can be used not with the collimated beam, but with the focus beam. And this is here picture of the proton microbeam, or nuclear microbeam or ion microbeam. So the ions are focused to sub-micron dimension to the sample at the sample surface, and as they can be scanned by a scan generator connected to the deflectors, you can make images of elements present in the sample, and this is a microscope image of one sample. So all these techniques that I was talking about last 10-15 minutes will be discussed tomorrow by three of my colleagues. I will just conclude with one for me nice story about when ion beam analysis techniques could give important information, and that is APOXIOMENOS statue that has been found 25 years ago at the bottom of the Adriatic Sea, and this is the original image of the statue that was been found by Belgian tourists at the depth of 40 meters. And after several years, the statue has been removed, and then it was used, that has to be restored. First 3 years in this desalinization process in order to maintain the structure of the bronze. And then later on with by mechanically polishing that they succeeded to make original shape, which is wonderful. And this statue is today exposed in the island of Lošinj in dedicated museum. So this APOXIOMENOS is the name comes from the athlete that is scraping his sweat by a small instrument. And so this is a very classical Greek sculpture, which have been also used by Romans later on. And then the main question was whether it is a Roman or a Greek origin. So the first and probably one of the most important was accelerator mass spectrometry. So this is another technique which we don't have in Zagreb, but is very known for the accelerator application. Accelerator is very similar as the one we have, and it is used to accelerate carbon-14 ions from the sample. And these samples can be very small, which was the case in this investigation. It was very small remains of wood and seeds that were found inside of the statue. And these wood and seeds have been dated to at least 2,000 years old, which means that the statue should be even at least 2,000 years old. So that is the first information which was very important. The second information was the composition of the alloy, and here was very important the PIXE analysis, because we can see that the concentration of the lead is quite high, and the Greek bronzes have very low concentration of lead. We had to test also is this lead concentration at the surface or interior of the bronze, and that has been shown here in this image when we do microbeam analysis of the section. And you can see that this part here on the left side has been exposed to the seawater, and therefore these parts have leached the copper from the bronze, and then the lead has been increased even to very high concentration, but never it was even inside of the body were always about 5%, which indicate that this is a Roman, but could be of Greek as well in extreme cases if that part is majority. Anyway, the most important finding was also done from mass spectrometry by lead isotope ratio, and this is not done by accelerator. This is with the ICP, high resolution ICP-MS. And what is also important to have the database, and you could see here. Here is comparison of our measurements with other sources of lead in ores close to grease, which is obvious very big difference. While when we compare the lead isotope ratio to the ores coming from the East Alps, which is the vicinity of basically of Rome, this is much better similarity. So in our case, our conclusion was that is APOXIOMENOS of Roman origin, but it seems that there are still a lot of art historians that don't use these results either intentionally or because of the higher value of Greek statue. Anyway, this is an example of one of our investigations. We have many such investigations during the year through CERIC or to other projects. And I just want to conclude the main, let's say, messages to everybody, what ion beam analysis can do. So we can analyze all elements from hydrogen to uranium. PIXE can analyze everything above sodium, but we can analyze also oxygen if needed. But ERDA and RBS can do all the elements. Okay, RBS cannot make hydrogen. And with nuclear reaction analysis, some specific light element isotopes can be measured as well. Most of these techniques have very high sensitivity, some bulk material, ppm levels are concerned. So PIXE can do most of the elements with the ppm levels. RBS and ERDA are more surface techniques, and they are analyzing 10 to 14, 10 to 15 atoms per square centimeter, in some cases even lower. But this depends on the particular specific analytical question. We often do silicon or diamond or many different materials which are of technological importance. And then up to, let's say, 10 years ago, all ion beam analysis techniques are basically either isotopical or elemental, but this new MEV SIMS that we have is molecular analysis, and as it can be combined by the microbeam, it can be very powerful for imaging of very small concentration of molecules inside of some small structures like a nuclei, like a living cell, not living cell, but cells or different objects. Generally, all the analysis techniques are not destructive, but one has to say that when we expose the sample to the beam, some materials can be heated, and because of this heat, they can be locally destroyed, but on very small levels. And of course, that is connected to microbeam analysis, because we can image typically down to 1 micron, but in some cases down to 200 nanometers, which was the best resolution we have obtained. So that is all from me. Well, I thank you for your attention, and I will accept questions if any. So feel free to ask me.